गुड आफ्टरनून बच्चों। आज हम कोलिगेटिव प्रॉपर्टीज के बारे में डिस्कस करेंगे। जैसा कि आपको मालूम है, अगर हम एक नॉन वोलेटाइल सोल्यूट लें, नॉन वोलेटाइल सोल्यूट दैट विल बी इन द सॉलिड स्टेट, और उसको हम मिक्स करें एक वोलेटाइल सॉल्वेंट में, volatile solvent that is a liquid, तो जो सॉल्यूशन बनेगा सोल्यूट प्लस सॉल्वेंट विल मेक ए सॉल्यूशन, एक होमोजेनियस सॉल्यूशन बनाएंगे हम। यानी एक नॉन वोलेटाइल सॉल्यूट को लेके हमने डिजोल्व किया एक वोलेटाइल सॉल्वेंट में, और उससे एक सॉल्यूशन बना होमोजेनियस। तो इस सॉल्यूशन की कुछ प्रॉपर्टीज होती हैं, दे आर कॉल्ड कोलिगेटिव प्रॉपर्टीज, और वो प्रॉपर्टीज के बारे में आज हम डिस्कस करेंगे। सो कोलिगेटिव प्रॉपर्टीज बेसिकली क्या है? दे आर द प्रॉपर्टीज शोन बाय द सॉल्यूशन prepared by dissolving a non-volatile solute into a volatile solvent. So non-volatile solute plus a volatile solvent that is in liquid state, इससे जो सॉल्यूशन बना उस सॉल्यूशन की कुछ ऐसी प्रॉपर्टीज होती हैं जो कि सोल्यूट के पार्टिकल्स, दैट इज नंबर ऑफ पार्टिकल्स ऑफ द सोल्यूट पे डिपेंड करती हैं। दीज प्रॉपर्टीज विच आर कॉल्ड कोलिगेटिव प्रॉपर्टीज, दे डिपेंड ओनली ऑन द नंबर ऑफ सोल्यूट पार्टिकल्स, दैट इज नंबर ऑफ मॉलिक्यूल्स ऑफ द सोल्यूट प्रेजेंट इन ए गिवन अमाउंट ऑफ solvent. यानी ऐसी प्रॉपर्टीज सॉल्यूशन की जो नंबर ऑफ सोल्यूट पार्टिकल्स डिजॉल्व्ड इन द सॉल्यूशन उसके ऊपर डिपेंड करती हैं खाली। दे डू नॉट डिपेंड ऑन द नेचर ऑफ द सोल्यूट। सो दोज आर कॉल्ड एज कोलिगेटिव प्रॉपर्टीज। इसके कुछ एग्जाम्पल्स हम दे सकते हैं, जैसे नंबर 1 इज लोअरिंग, दैट इज रिलेटिव लोअरिंग ऑफ वेपर प्रेशर। व्हाट डज इट मीन? दैट मीन्स व्हेन वी डिजॉल्व ए नॉन वोलेटाइल सोल्यूट इनटू ए सॉल्वेंट, then the vapor pressure of the solution will become less than that of the pure solvent. So that is why we say relative lowering of the vapor pressure. That means the vapor pressure of the solution becomes less than that of the pure solvent. Number 2 is the elevation in boiling point. Elevation in boiling point. Why the boiling point increases? Because the vapor pressure comes down, that means the boiling point will increase. So solution vapor pressure has got reduced, that is why the boiling point of the solution will increase than that of the pure solvent. And number 3 is the depression in freezing point. So depression in freezing point is another colligative property. That means the freezing point of the solution will become less than that of the pure solvent when we dissolve some non-volatile solute into the solvent. And number 4 is the osmotic pressure. Osmotic pressure. What is osmosis? Osmosis is nothing but the movement of solvent molecules through a semi-permeable membrane towards the solution side, or we can say the movement of the solvent particles from a low concentration solution to a higher concentration solution. So we will discuss in detail later on. So today we will discuss one property, the first property, that is relative lowering of vapor pressure. So what happens, suppose we have a volatile liquid that is called the solvent. So this is the solvent in this closed container. Let us call it number 1. Okay, and the solute is number 2. Solute we will denote as 2 and solvent as 1. So this will have the particles of 1, all particles of 1, because only solvent is present here, and this will exert a vapor pressure, say P1 naught. P1 naught is the vapor pressure of pure solvent. Okay, now I mix some non-volatile solute into this solvent. So now the molecules which are present will be of solvent plus solute, which is non-volatile. Okay, and here it was only solvent. Now what will happen? This will exert some vapor pressure that we denote by PS, where PS is the vapor pressure of the solution. Okay, now because this is solute is non-volatile, so this will cover a part of the surface of the solution. Suppose it will have the particles of 1, 1 and some 2, 1, 1, 2, like this. So particles of solvent as well as solute will be present at the surface of the solution. So what will happen? Now this surface is partly occupied by the molecules of the solute, which is non-volatile. So this part of the surface which is occupied by the non-volatile solute will not allow the molecules of solvent to pass through the vapor state. They cannot escape to the vapor state because this part of the surface of the solution is covered by the molecules of the non-volatile solute. So what will happen? This PS, that is vapor pressure of the solution, will become less than P1 naught. Okay, that is the vapor pressure of the pure solvent. Now how much it will come down, that we can estimate by the Raoult's law, which says that the vapor pressure of the solution is nothing but vapor pressure of pure solvent, that is P1 naught, multiplied by the mole fraction of the solvent present in the solution, that is say X1. So this is one formula, that is when we dissolve some non-volatile solute in a solvent having vapor pressure P1 naught, then the vapor pressure of the solution will become equal to P1 naught multiplied by X1, where X1 is nothing but the mole fraction of the solvent present in the solution. Okay, now this formula we can again write as P of solution equal to P1 naught into 1 minus X2, where X2 is the mole fraction of the non-volatile solute. Okay, so solvent mole fraction is X1 and solute mole fraction is X2 in the solution. So this we can write as P1 naught minus P1 naught into X2, or we can rearrange this and we can write as P1 naught minus PS upon P1 naught is equal to X2. Okay, for this we can write this is equal to X2. That is called the relative lowering of vapor pressure, because the vapor pressure of pure solvent minus the vapor pressure of solution, that is the decrease in vapor pressure divided by the original vapor pressure of the solvent. So this is called the relative lowering of vapor pressure, which is nothing but equal to the mole fraction of the non-volatile solute present in the solution, and this will be nothing but number of moles of solute divided by number of moles of solute plus number of moles of solvent. This is the value of x2. Okay, so this is how we can determine the vapor pressure of the solution prepared by dissolving a non-volatile solute into a volatile solvent, that is given by this formula. Now let us understand this graphically, how this vapor pressure is reduced. Okay, suppose if I plot this vapor pressure versus say temperature. Okay, now suppose this is the curve for pure solvent. Okay, that is pure solvent. Then the solution will have this curve like this. So this is for the solution having non-volatile solute present in the solution. So what we see here, suppose I draw a line like this. So the temperature, suppose this is the atmospheric pressure, 1 atmosphere. Now you see what is the effect on boiling point. If you see the effect on boiling point, then at this, for the solvent, this is the boiling point. Okay, and for solution, this is the boiling point. So the boiling point of solution has increased by this amount, okay, as compared to that of the solvent. So we can say that as the vapor pressure of the solution comes down by dissolving a non-volatile solute into a volatile solvent, and in the same way the boiling point of the solution will become higher than that of the pure solvent, and this is called the elevation in boiling point, that is delta TB. Okay, and this is nothing but small m into Kb, where Kb is the modal elevation constant and it is specific for all given liquids or solvents, and small m is the molality of the solution, which is nothing but the number of moles of solute present in 1 kg of the solvent, that is number of moles of solute per kg of the solvent, that is molality. So this is how we can say these two colligative properties we have discussed today. One is the relative lowering of vapor pressure, and second is the elevation in boiling point, because both are related. As the vapor pressure of the solution comes down, the boiling point of the solution will increase accordingly. So with this we conclude, and we will discuss in detail in the next session. Thank you.